Alright students, today we're doing section 2.6 Scatterplots and best fitting lines. This is going to be a different looking video than normal and it's pretty hard for me to tape. I have this thing over here, I have this thing, your calculator over here, and then even later on I'm going to pull up a PowerPoint. It's a lot, so let's see if I can make it through. Alright, the essential question for today is, how do I model a line of best fit to predict paired data? So here's the deal. What we had been doing is we had been doing lines like this, y equals 2x minus 4, and if you really knew how to use your graphing calculator really well, you could come over here, you could turn it on, you could go up to the y equals menu, you could plug that bad boy in, and then you could graph it, and it would graph a nice straight line. That's what you did on the quiz, you know how to graph lines. The thing is, in a line, every single point is exactly on that line. No points are off the line. It's not very real world. There are no exceptions on this line. Every single dot is on it. If I had a point like over here, that's just not on the line. It's not in our equation. So what we're doing today is we're going to be thinking about real world data when things aren't quite so clean as a perfectly straight line where all the points are on a line. So let's look at our one example that we'll be doing today. And let me just zoom appropriately so you can see it. All right, here's what we're doing in this section. Texas. There's a state I haven't been to, but it's a famous one. People eat a lot of food down there. I'm totally stereotyping, so forgive me. But right here, this chart, if we read it, it says the following data represents the population Y of Texas. Okay, in millions, so these Y values are the population of Texas for various years after 1997, so that's the X. So it looks like in 1997, for example, the population was 19.7 million people. Whoopee. They probably all play football and eat big steaks and do Texas things. Now, let's look at what these points look like on a graph because they're not in a perfectly straight line. People do not multiply, I guess. The population is not going to grow in a perfectly straight line. So what I can do is this. Let's come over to my calculator. I'm actually going to delete this out of the y equals menu real quick. Okay. Here's how you're going to put these points into your calculator so your calculator can make a graph for you. Doesn't that sound exciting? First, you're going to click on Stat. Okay. Then, you're going to click on Edit. Okay. You just hit Enter because you had Edit selected. It brings up these super nice lists. Hey, there's Texas. We're talking about that right now. Awesome. There's the shape of Texas for all you who don't know it. Now, in our list 1, I'm going to put the X values, okay? So 0, 1, 2, 3, 4, 5, 6, and it looks like I go up to 7. In list 2, I'm going to put the corresponding Y values. So next to my X of 0, I need to put 19.7. Next to 1, I'm going to put 20.2, and so on. Let's see how quick I can type these in. 21.3, 21.7. Okay. Wait. Okay, I can do this. Perfect. All right, so I have my two lists. I have my X list and my Y list. Now, we want to see our calculator make a graph for us. So again, I'm going to go through these instructions real quickly. You can always pause and rewind if you miss something. You're going to hit second, Y equals. So that means stat plot. Okay, so second stat plot. You're going to hit enter to look at plot 1. You're going to turn plot 1 on, make it this type. We want it to be a bunch of dots. And then down here you can see the X list is list 1 and the Y list is list 2. That's where we put our X's and our Y's. And you can make the dots any shape you want. Let's make it this box. That sounds fun. Now, you're going to have to do one more thing. If you graph right now, your graph is not going to show you the correct scale of axes. So let's click on Zoom and go all the way down to Zoom Stat. That will zoom to where our list is. Let's hit Enter. Oh, there it is. Now, as you can see, along the x-axis, we have the years, and this is really exciting for me because I love making graphs. Along the y-axis, we have the population in millions, and as we can see, as the years go along, the people go up. But if you look really close, you'll notice that these are not in a perfectly straight line. They're just not in a perfectly straight line. So if I were to try to make an equation of a line like I tried to do on the quiz, like put 2 points into point slope form, whatever, it wouldn't work out right because these points are not on a straight line. Luckily, my calculator can draw what is called a line of best fit for this data, and I'm going to show you what that means as soon as we do it. So here's how you make, and this is part A, write a linear equation to model this data. Let's click on Stat. We're making a line of best fit. Arrow over to Calc, and arrow down to LinReg, which is not the name of some reggae artist who's a female. It stands for linear regression, which is a synonym for line of best fit, which is what we're making here. I'll hit Enter. X list is list 1, Y list is list 2. Don't worry about these. And calculate. Okay. So here's the deal. Here's what it gives me. This is our linear model for the data. It says y equals ax plus b. That kind of looks like y equals mx plus b, right? And it tells me my a is 0.39, blah, 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 and my b is 19.758, blah, blah, blah. So what we want to do is we want to plug the a in where it says a and the b in where it says b. So that's y equals 0.390x plus 19.758. Let's just do 3 decimals for today. This is the equation of a line. It looks weird, but here's the slope and here's the y-intercept. And let's look at what the calculator shows. Let's go back to my y equals menu. I'm just going to put this line in real quick. 0.390x plus 19.758. And when I graph this line, you're going to see, look, it goes about right through the middle of the dots. Is it hitting every one exactly on? No. This guy looks a little below. This guy looks a little above. But it's making kind of the best fit line that goes right through the middle of the data. So that's our best fit line. And I can use that line to do things like part B. Predict how many millions of people will live in Texas 8 years after 1997. Let's pretend I'm living back in the 2000s. I don't know what the population of Texas is going to be 8 years after 1997. Using this data and my best fit line, I can do what's called extrapolation, which is to predict a future value. Remember, this 8 years represents an x. So if I plug into my equation 0.390 times 8 plus 19.758, the y value I'm going to get back is my prediction for how many people are going to live in Texas in the 8th year. So let's do that real quick. 0.390 times 8 plus 19.758. All right, they're predicting that in the 8th year after 1997, 22.878 million people are going to live in Texas. Is that consistent with where year 7 was? Yeah, it's just a little bit more than year 7. Very nice. Now, the next thing I want to talk about is the correlation coefficient. However, I'm a little bit distressed because I don't think my calculator emulator is quite as good as your calculator. If I go back to that place where I did the linear regression, where I got that equation, I put it in again. It tells me my A and my B, but I think most of your calculators should also say something like R equals. R is the correlation coefficient, and if I were to estimate this correlation coefficient, I'd say it was somewhere around let's say 0.91. That's the correlation coefficient I would predict your calculator would tell you, but for some reason my emulator is not coming up with that data, so we'll check to see if it's on your calculators in class. Now, I need to explain what the correlation coefficient means. So let's transition over to my PowerPoint. All right, here I am in PowerPoint land, and this slide is about different values of the correlation coefficient R. So Remember what I just said, that I predicted my correlation coefficient was something like 0.91. If you just take a brief look at this slide, notice we have -1 all the way down here, we have 0 in the middle, and then we have 1 at the top. These are all the values the correlation coefficient can be. It never goes lower than 1, so that doesn't work. It never goes higher than +1, so that doesn't work either. The correlation coefficient is always in between -1 and 1. Basically, the more close to 1 it is, the more in a perfectly straight line our dots are. So with my Texas data, the dots were all really close to the line, which is why I selected a very positive, very close to 1 correlation coefficient. Notice at 1, if I were to draw my line of best fit right through these points, they would all be exactly on the line, and that's why it's +1. That means everything is perfectly on a line. When you get lower though, that means there's definitely still a positive correlation, and if you were to draw the line through, it would definitely be positive, but increasingly more and more points are off the line. Like look at point 7. There definitely is a positive correlation, meaning if I drew the line through there, it'd have a positive slope, but a lot of points aren't on the line. By the time you get down to 0, I don't even know where to draw my line. Like, should I draw it this way? Or should I draw it this way or this way? I can't really tell because the points are so scattered. Basically, there's no coefficient of there's no correlation at all. As we get more and more negative, we can see that there is a definite downward slope, negative slope, until you get a really high correlation coefficient. -1 means everything is on an exactly straight line that is falling. Let's look at some examples. For this data, what would you estimate R to be? If you were to draw your line through, kind of like that, through the middle of the points, what would you predict R to be? I don't know, Mr. Gregory, what's R? Hey, it's 0.82, so notice it's positive because my line is going up. It's pretty close to 1 because most of these points are pretty close to the line, but it's not 1 because there are some that are off the line. Another example, I draw my line through here, so I know my R had better be negative. Let's say negative 0.84. Oh, negative 0.7. So again, it's like pretty high because the points are pretty close to the line. It's negative because I would draw my line going down, but it's not -1 because they're not all right on the line. How about this one? Oh boy, where in the world do I draw my line? I'm saying 0 because there's no correlation at all. I was right. Go me. Here are some other ones. Notice, for example, A, I have a positive 0.82 correlation. For B, I have a negative point. Is that the one we just did? Yeah, it totally is. Let's talk about D. D and E, there's definitely a pattern, but it's not a straight line pattern. Like, how would I draw a straight line through? I don't know. This one looks like a smiley face, but I wouldn't know how to draw a straight line through here. So these have 0 R values. Let's just review. I can use line of best fit to kind of predict my values. That's what I did for the Texas equation. The coefficient, the correlation coefficient R, behaves in this way. If it's 1, it's in a perfectly straight rising line. All of the points are right on that line. 0.5, it's definitely positive, but some of the points are off. 0, there's no correlation at all. And then the negatives, -0.5, it's a little negatively correlated. -1 means everything is on a perfectly straight falling line. Guys, thank you so much for watching, and I'm excited to apply this stuff in class because this is the real world stuff.